Hi, hello and welcome to Bonding with Lewis Diagrams. I thought that making a video for this section might be helpful for Thursday's quiz, so feel free to fast forward, rewind, pause, whatever you need. I'm going to go over about one of each here to try to help the people that need some extra review time, so check it out. So drawing the Lewis diagrams. I started out here, this is sodium is what we're going to begin with, and it actually looks like this over here. It's a real interesting metal. It's kind of like a stick of butter in consistency almost, but it's a metal, and you can see when put in water, it reacts really violently. So how do we draw a Lewis diagram though? The first thing you need to do is have a periodic table handy. We're going to refer to it a lot in this. I've got a nice little pop-up periodic table here, and we're going to find sodium. It's over here among the alkali metals. The nice thing about the periodic table is the organization. And so we can see that sodium's got 11 electrons in total. Of those 11, 2 of them are going to be put into the first energy level. And so we've got 9 remaining. In the second, we can hold 8. So we subtract another 8. And that leaves me with one final one in the third energy level. Those are my valence electrons. That word valence is a really important term for this section, and being able to determine the valence electrons is critical when making Lewis diagrams. So we've got one valence electron for sodium. Around the symbol then, you're going to put one single dot to show that one valence electron. Moving on. So the valence electrons, this is the trend that we really need to learn. In the columns, right, going up and down, the number of valence electrons is the same. And so we know sodium, we just found it as one valence electron. That means everything in the alkali metals over here, hydrogen all the way through francium, have one valence electron. The way the periodic table is set up, we go right down along this line. So we've got 2 valence electrons in this column. Over here, we're skipping the transition metals. These ones we're not going to have here. These are the transition metals. The next one is boron then. Boron, we've got 3 the whole way down. Carbon, we've got 4 valence electrons the whole way down. 5, 6, 7, and then 8 over here with the noble gases. The key to remember for bonding is that 8. All right, the magic number is 8. A full outer shell is what each of these elements are going to want. And so we can look at how many valence electrons they have and kind of guess what they're going to do in bonding, because they all want to have a full outer shell. Everything from carbon over, right, this group over, these ones all are going to try to gain electrons because they're close to 8 already. If they get a few more, they're going to be right where they need to be, and they'll be very satisfied. Everything to the left of it, right, all the way over here to the alkali metals, all of these are looking to lose electrons because they are less than halfway there. It's easier to lose a few than gain a whole bunch. Because they're going to lose, that means they're going to form positive ions, right, with a positive charge. As they get rid of electrons, they'll have more protons. The ones over here that are gaining, those are going to be negative ions. All right, so those are some trends that are really helpful, things that we've kind of built up in previous sections that will pay off for this section. So the first thing we're going to look at is the Lewis diagrams, and we've got a couple of them here to do. Make sure you've got a periodic table handy. It's going to make this a lot easier. So the first one here is neon. Neon is number 10 on the periodic table, 10 electrons in total. 2 of those are going to be buried in the first energy level. The remaining 8 are going to be in the second energy level. And so when placing the electrons, I like to place them kind of like a compass, north, east, south, west, and putting them in their little spots. Oops, there's one, and there's one. And so there's my 8 valence electrons, right? A compass looks kind of like this, north, east, south, and west. It is very important to place them the way that I'm placing them because it shows you what's available for bonding. If we've got a pair of electrons, like we've got a pair of electrons at each available spot in neon, that pair is not available for bonding. Whether it's ionic or covalent, it cannot be used. If we look at hydrogen, hydrogen's number 1. It's got 1 valence electron. That unpaired electron, that one can be used for bonding. There's no more electrons here, so that's the only one it's got to bond with. If we brought neon and hydrogen together, there's going to be no bonds formed because neon's got 2 electrons at each possible zone. It can't take any more. Let's look at oxygen. Oxygen has 6 valence electrons. We'll go 1, 2, 3, 4, 5, and 6. Sorry about that last little dot there. When I draw it with the northeast, south, and west arrangement, we've got 2 unpaired electrons. Let me round them out a little bit. These 2 spots are available for bonding, and if we brought an oxygen and a hydrogen together, you can see they each have an unpaired electron. This is a potential for a bond, and right, something would happen between them. There's a few more down here. I'm going to run through them pretty quickly. Silicon has 4 valence electrons, so we would have 4 dots around the outside. 4 unpaired electrons means it has 4 spots it can bond for. Lithium's got 1 outer electron, and carbon is going to be similar to silicon. They're in the same family. It also has 4 valence electrons. If I look at, let's say oxygen, we're going to focus on oxygen up here. If I look at oxygen and it's 6 valence electrons, these 2 empty spots, right, here's an empty spot and here's an empty spot, those 2 empty spots need to be filled. And so when we start doing ionic bonding, that should be a good clue to you that it needs to add 2 more electrons, right, in those empty holes. They need filled up. So we're going to add 2 electrons. When we add 2 electrons, the total charge of oxygen is going to become more negative, and so it'll pick up a -2 charge. Something like hydrogen, or let's actually look down here to lithium. Something like lithium, it's going to have 7 empty spots around here. That's a lot of effort to fill, so it's going to get rid of that electron, right? It's going to move it on, and so we're going to lose 1. When we lose 1 electron, it's going to pick up a positive charge. So our charge on lithium, when it forms an ionic bond, would be +1. Ionic bonding. This is a transfer of electrons. All right, we're going to be transferring electrons here. Anytime there's an ionic bond happening, it's going to be between a metal and a non-metal. It is the only circumstance you can have a ionic bond. So the 2 we're going to do are magnesium and sulfur. Let me pull up the periodic table quick here. Magnesium falls under beryllium. Remember, this is a 2 on top, so we've got 2 valence electrons. Oxygen is at the top of its family here. This family has 6 valence electrons. These 2 numbers are critical for this. If we didn't have these right, our drawings would not work out properly. So let's make our Lewis diagrams. We're going to have 2 and 2. I was looking at oxygen before. Let's go back and find sulfur. Sulfur is directly below oxygen, so it also has 6 valence electrons. All right, so we're okay. So we've got 2 valence electrons on magnesium and 6 valence electrons on sulfur. 4, 5, 6. And so now we're looking to transfer them. We're trying to move electrons here, and the way that they're going to move is to fill up that outer energy level. The easiest way for sulfur to fill up its outer energy level would be to gain 2. Notice we're missing 2 here. We've got 2 unpaired electrons. They each need a buddy, so we need to add in 2 more. Magnesium only has 2 electrons. Let me round this one out a little better. Those 2 electrons are on the last shell. It's too hard to gain 6 for magnesium, so it's going to try to give away 2. And so when these 2 come in contact, we're going to pass 1 electron over here, and we're going to pass 1 electron over here. When we pass those both over, now sulfur's got full 6 electrons. We've added 2 negative charges to it. Each of those electrons is a negative charge, so its overall charge becomes -2. Magnesium has lost 2 electrons to have an empty outer shell, which means it reverts to the next one down, right? Magnesium is going to fill up that next shell, and so it has 2 more protons than electrons, so its charge is a +2 charge. I mentioned the crisscross method in class. We can crisscross the charges, right? We crisscross them down, we take the 2 and we take the 2, and we end up with the formula Mg2S2. These 2's can simplify out then, right? 2 is divisible by 2, so we'll simplify it, and we get Mgs, right? We only need 1 magnesium. There's my 1 magnesium. For every 1 sulfur, there's my 1 sulfur. And so here is our resulting chemical formula. That is ionic bonding, all right? When we're transferring electrons, we have charged particles. Because of those charged particles, they can conduct electricity when we dissolve them in water, right? This negative charge and this positive charge are going to be very conductive when you break them apart into these ions. All right, the next step I'm going to show you are covalent bonding, and in covalent bonding, we're sharing electrons. A covalent bond only happens between nonmetals. So this is a non plus a non. There are no metals involved in covalent bonding. There we go. Non plus a non. So the first one we're going to do is over here, H2. You're always going to get a formula for covalent bonding because we've got a couple different options when we make these. We can make single, double, and triple bonds, but it's going to start the same way that we started the ionic bonding with Lewis structures. So let's look at hydrogen. All right, let me get my two H's down here because I know I've got two hydrogens. The first thing that we want to do is find the total number of valence electrons in the formula. And so because I've got two hydrogens, my total number of valence electrons is 2 electrons. All right. Each hydrogen has 1. I can even draw them if I want. Each hydrogen has 1. So we've got a total of 2. The next thing we want to do is create the skeleton. And so the skeleton is going to be a single bond represented by a line between the two hydrogens. All right. And that would look like this. That bond, and every single bond we do, every line between two different atoms is worth 2 electrons. And you saw I had one on the left, I had one on the right, and I simply connected them together. So I've used up 2 of my electrons. All right, that means I've got 0 remaining. At this point, because I'm out of electrons, I need to look at their energy levels and do they have enough electrons to fill up that last outer shell. My hydrogen on the right has access to 1, 2 electrons, right? That bond allows them to share the electrons over it. My hydrogen on the left, let me switch colors again here. My hydrogen on the left also has access to 2 electrons, 1, 2. So they both have a full outer shell. That means them both very happy, right? And we have formed a covalent bond. H2 is probably about as simple of a covalent bond as we can do. Let's look at H2O over here. So for H2O, again, my very first thing I want to do is find total number of electrons. Hydrogen, you just draw them again quick here. Hydrogen has 1. My second hydrogen will also have 1. My oxygen will have 1, 2, 3, 4, 4, 5, 6. All right, so now that I've made my Lewis structures, I can figure out how many total electrons I've got. I've got 1, 2, 3, 4, 5, 6, 7, 8 total electrons for H2O. So I need to make sure I've got 8 electrons in my final drawing. The next one we need to do is build our skeleton. So anytime you've got fewer of 1, and I only have 1 oxygen here, that should be the center of the skeleton. The other things, the hydrogens especially, are going to be kind of branches off that central atom. So H, H, and I'm going to create my skeleton. Remember, I used 2 electrons for each one of these single bonds. There's 1, and single bonds. So at this point, I've used up 1, 2, 3, 4 of my total electrons. So let me subtract them off my count, meaning I've got 4 electrons remaining. At this point, I need to place these electrons in pairs onto my atoms. Now, the thing that you need to be careful with is hydrogen, being the special case that it is and can only take 2 valence electrons, I can't put any more there. So my 4 remaining are going to have to go on oxygen. And I always put them in as a pair, and we may need to split them up later, but let's put them into a pair. There's 2 of them, there's 3, there's 4. All right, and so I've used up my remaining 4 electrons. I'm down to 0, which is where I want to be. At this point, we need to count up the valence electrons on each atom and make sure that they have the correct number. So I'm going to circle them. I'm going to use a different color each time. So let's start with, we'll start with white. So hydrogen over here, we've got access to 2 valence electrons. Hydrogen is satisfied. My next one, I'm going to do the hydrogen on the left, or the hydrogen on the right, sorry. And again, it's got 2 valence electrons, so it's got a full outer shell. It is also satisfied. The remaining one to look at is oxygen. How many electrons on oxygen? I've got 1, 2, 3, 4, 5, 6, 7, 8. And so if I were to circle all of oxygen's electrons, it would be all of these ones. And so that is a total of 8 electrons, meaning all these atoms are happy. And so we've got a correct covalent compound of water, H2O. It can get a little more advanced than this, and so the next one here, CO2, is going to take it a little bit further. Just like before, we're going to look at the... Alright, so this one will be a little more advanced. This is CO2, carbon dioxide. We've got a carbon and 2 oxygens. So first thing I need to do is figure out total number of electrons. Carbon's got 4. There's my carbon. Oxygen has 6. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. I apologize for those electrons. Some of them are not very circular. It is what it is. 4 plus 6 means I've got 16 total valence electrons to use up. And I need to make sure I put all of them in the drawing. Again, I've got 1 carbon atom, so that needs to be my central. I'll put the oxygens on the outside. Next step is to build the skeleton. So here's my single bond connecting each of them. And there's a dot. There's a dot. Remember, 2 electrons for each single bond here. And so I've used up 4. So I'm going to subtract 4 electrons. That means I've got 12 electrons remaining that I need to place in the drawing. A good habit is to place those remaining electrons around the outside on the oxygens here, the outside of the molecule, before you start placing them on the central one. And you'll see why in a second. So let's use them up. 1, 2, there's 2 of them. 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And so I'm out of electrons at this point. And so now we need to check, are all the atoms happy? Well, oxygen on the left here is pretty happy. 1, 2, 3, 4, 5, 6, 7, 8 electrons around it. So oxygen's good. 1, 2, 3, 4, 5, 6, 7, 8. This one is satisfied as well. The problem here is carbon. Carbon only has 1, 2, 3, 4 electrons. So it's not going to be satisfied right now. And what we're going to have to do is we're going to have to make some double bonds. All right, I'm going to write that up here real quick. A double bond is simply a second line where we already have a single bond. And so in order to do that, remember, each line requires 2 electrons. So in order to do it, I need to get rid of 2 electrons from an oxygen. So here we go. These 2 are going to make up my double bond. It doesn't matter which 2 from the oxygen I pick. I saw them first, and so I'm using them. And so these 2 electrons are going to become parts of my double bond. And there they are. We formed a double bond. Carbon now has 1, 2, 3, 4, 5, 6 electrons. It still does not have enough, so we're going to have to do it a second time. And X these 2 over here. And we're going back to green to create a second double bond. Right, like that. And now carbon's got its full 8. Oxygen also has full 8. 1, 2, 3, 4, 5, 6, 7, 8. Same is true for both sides. So we have a satisfied molecule here. All of them are happy. And so that is a quick rundown of bonding. It's up to 18 minutes for the video right now. Please feel free to fast forward, jump around as need be. This is meant for you to have a review tool. If you get stuck on one, feel free to refer back to this video and use it to help you with your homework or as you review for the quiz. Please ask any questions you've got in class, and thank you for watching.